So in this class, we will see some more code converters. Okay, the same topic we can continue like previous topic. Like it's a again code converter only. We'll see few more examples of code converter. Like here, the question would be like this: design a code converter which converts. So the question is design a code converter which converts 4-bit binary 4-bit binary to 4-bit gray code. Okay, so this is your mainly the question. So how to do this? As I have told you, this is again a code converter is again a combinational logic circuit. Obviously here it's clearly mentioned to you 4-bit binary to 4-bit gray. Okay, so in this case what you need to do, you would have 4 inputs here. Each input takes 1-bit binary data, and at the output it has again 4 bits. Those outputs also has 1 bit each. So obviously we would have to design a code converter which converts 4-bit binary to gray. 4-bit binary to gray code. Okay, so here it has 4 bits: 1, 2, 3, 4. Those 4 bits are binary bits, which like is B3, B2, B1, B0, and outputs are again 4 bits: G3, G2, G1, G0. Understand? So this is basically the design we are going to do. What is the design we will see today? So here you can obviously come to know that first you need to understand the problem statement. The problem statement is you need to design a binary to gray code converter, each of 4 bits. Okay. Next, you need to assign the letter symbols like B3, B2, B1 for inputs, the G3, G2, G1 for outputs. This is your inputs and these are your outputs. Now what you have to do, fourth step for combinational logic circuit design, you have to construct the truth table. For constructing the truth table, what you need to do, you need to know the behavior. You need to know basically how a binary code would be converted as a gray code. That is important. Okay, so how a binary code will be converted as a gray code, I have already told you. So what you need to do in this case, mainly let's say you see here 0 0 1 1. So I'll give an example just. So this is your binary code, 4-bit binary code. So in order to convert it to the gray code, what you need to do, you just need to copy the MSB. This is your MSB and this is your LSB. So you just need to copy the MSB as it is. Then you need to perform the XOR operation between these two and write the result here. 0 and 0. What is XOR operation? If it is AB, XOR operation is A XOR B, which is nothing else. 0 0 0 0 1 1 1 0 1 1 1 0. So this is your XOR get truth table. Okay, so now if we perform 0 0, you will write a result here. So what is XOR? So this is 0. Next you perform XOR operation between these two. 0 1, write result here. 1 1 1, write result here. XOR operation 0. This is the way you need to convert. Now you can take another binary code. Let's say 1101 is a binary code. Again you need to convert a gray code. Means what you need to do, you need to just copy the MSB as it is, and next perform XOR operation between these two. 1 1, what is XOR operation? If you do it, it's a 0. 1 0 XOR operation is 1. 0 1 XOR operation is 1. So this is your gray code of a binary. Okay, this is the way this is the behavior of your, this is the behavior required to construct the truth table. Okay, so you come to know about it, the behavior. Now you can construct the truth table. How to construct the truth table? Very simple. You would have inputs here, binary coding input B3, B2, B1, B0. As I told you, it's a 4-bit input, so it's a binary code and it's a input. Okay, this I'm doing the truth table, and now at the output we would have G3, G2, G1, G0. Okay, this is my output, which is actually a gray code. Okay, any doubt on this, students? Okay, so next what you need to do, it has 4 inputs, means obviously 2 to the power 4, 16 number of combinations can be possible. For that case, what you need to do, you would have 16 combinations: 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1. Okay. So next next 1 triple 0, 1 0 0 1. Next 1 0 1 0, 1 0 1 1, 1 1 0 0. Next 1 1 0 1, 1 1 1 0, 1 1 1 1. Okay, like this way you can just construct your truth table. Okay, after that you know that how you can do your gray coding. Just simply copy the MSB as it is. This is your MSB bit and this is your LSB bit. Similarly here, this is your MSB bit, this is your LSB bit. Okay, for this you just need to copy here, and next you perform the XOR operation between these two, 0 0. Whatever result comes, that is your G2. So 0 XOR 0 is 0. Next 0 XOR 0 is 0. 0 XOR 0 is 0. So this is the gray coding. Like this way you can just has to do all this. So this is also 0 0 0 1, and for this 0 0 1 0 would be, here we have already done 0 0 1 1. 0 0 1 1 will be your 0 0 1 0. So like this way you just has to construct. Next, copy MSB as it is, perform XOR operation 0 1 1, 1 0 1, 0 0 0. Okay, like this way. 0 1, you just has to copy MSB 0 1 1, 1 0 1, 0 1 1. Okay, next 0 1 1 0. For this, what you need to do, copy MSB as it is, 0 1 XOR 1, 1 1 XOR 0 1 0 1. Okay, next copy 0 as it is, 0 1 1 1 1 0 1 1 0. So this is the way you need to construct all your truth table completely. Okay, so next 1 triple 0, it will be copy MSB as it is, 1 1 0 0. Next copy MSB as it is, 1 0 1 XOR 0 is 1, 0 x 0 is 0, 0 XOR 1 is 1. 1 copy MSB as it is, 1 0 1 0 1 1 1 0 1. Next copy MSB as it is, 1 0 1 0 1 1 1 1 0. Copy MSB as it is, 1 1 0 1 0 1 0 0 0. Okay, like this way you can construct everything. Next copy MSB as it is, 1 1 0 1 0 1 1 0 1. Next copy MSB as it is, 1 1 0 1 1 0 1 0 1. Copy MSB as it is, 1 1 0 0 0. Okay, so this is the way you can has to do the truth table. After this, what you need to do, the fifth step for designing any combinational logic circuit, you need to find out the logical expressions. So logical expressions of what? Logical expression of all the outputs. So here you have how many outputs? 4 outputs. So you need to find out G3, you need to find out G2, you need to find out G1, and you need to find out G0. Okay, these all 4 outputs are, you need to find out the logical expression. How to find out the logical expression? You can construct the k-map. So in order to construct the k-map, what you need to do, it has 4 variable k-map. So obviously you can do this. I'm just going to do one, other you have to do. So this is your G3. So G3 would be constructed, and what are the input variables? The input variables are here. Don't change the sequence B3, B2, B1, B0. If you change the sequence, the result will come ulta. B1 B0, B1 bar B0, B1 B0, B1 B0 bar. Okay, similarly B3 bar B2 bar, B3 bar B2, B3 B2, B3 B2 bar. Okay, now you know the place values here. The place values are 0, 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, 12, 13, 14, and 15. Now put those minterms over here. So what is my G3 minterms which are present? All these after 8. From 8 onwards, all are present. Okay, am I correct? Friends, from 8 onwards. So here, this is present, 9 is present, 10 is present, 11 is present, 12, 13, 14, and 15. Everything else not present. Means it is all are 0. You can put 0 or you cannot put 0 also. The same meaning. Now what you need to do, you start grouping. So this is what you have to do. You can group it a single grouping, that is 8. All 8 minterms you can group it like this. So from this what you got, actually you have got it here B3. So what do you understand from this? G3 is equal to your B3. Obviously, why G3 is B3? You can also see what we are doing. We are just copying this B3 over here for G3. Okay, that's why obviously G3 will come as a B3. Understand? Or any doubt, student? This is very important question. Next, what you need to do? You need to construct the same. You need to find out the G2. For G2, again, you need to construct a KMF. So for this also, you need to construct a KMF from this. So I'll just do this. After that, you need to do the next problem. So this is again a 4 variable KMF. B3, B2, B2, B1, B0, B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Okay. So this B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. So you know the place values, accordingly you just put those values over here. So here it's present every 4 alternate values. Okay, here first 4 bits 0, 1, 2, 3, 0. Next 4, 5, 6, 7, 1, 8, 9, 10, 11, 1. Then finally again it's 0. So what you need to do? First 0, 1, 2, 3. All these are zeros. Okay. Next 4, 5, 6, and 7. After that 8, 9, 10, and 11. Other places all are 0. Okay. Now what you need to do? You just need to combine this. In order to combine, this is one more, this combination, and this is another combination. From this you got B3 bar B2. From this you got B3 B2 bar. If you do this for G2, which is actually B3 bar B2 and B3 B2 bar, so you got here B3 XOR B2. Understand? G2 will be B3 XOR B2. Similarly, you can find out for other values G1 also. If you have any doubt, please unmute and ask students. So again, G1, for finding out G1, you will be having again 4 variable KMF, which is having input variables are B3, B2, B1, B0. So which are actually B3, B2, B1, B0. So this is B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Next to B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. Now you put those values as we have seen here. How is it? First 0, 0, 1, 1, 1, 1, 0, 0. 0, 0, 1, 1, 1, 1, 0, 0. Next 0, 0, 1, 1, 1, 1, 0, 0. 0, 0, 1, 1, 1, 1, 0, 0. Understand? Now you can just map it. So mapping, this is one group. Okay, and this is another group. Okay, so we've already studied all these things in the KMF. So for from this we have got it as a B2 B1 bar, and from this we got as a B2 bar B1. Okay, so finally we have got G1 as B2 B1 bar and B2 bar B1. From we can also write it as B2 XOR B1. Okay, like this way you can find out also G0. The same way you can just has to construct again a 4 variable KMF here. Very simple. Okay, just has to construct 4 variable KMF and take the variables as B3, B2, B1, B0, and take this as B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Next is similarly B3 bar, B2 bar, B3, B2, B3 bar, B2, B3, B2, B3, B2 bar. Okay. Now put those values over there. How is it? Every alternate 0, 1, 0, 1 like this. 0, 1, 1, 0, 0, 1, 1, 0 like this. So you just has to put those values here. 0, 1, 1, 0, 0, 1, 1, 0. 0 1 1 0 0 1 1 0. Okay, so now you can map it up. This is one grouping, this is another grouping. So from this you have got b1 bar b0. From this you have got b1 b0 bar. From g0 will be your b1 bar b0 b1 b0 bar. Okay, now you got it as a b1 XOR b0. Okay, so all the statements you have got, all these g0 g2 g3 g1, all these values you have got. Next step is what? You need to construct the logic design. So your logic design would be just as simple as it is. So how is it? So we know that g3 equal to b3. Okay, so your inputs are what actually? B3, B2, B1, and your B0 are your inputs. Okay, so you know that you would have B3 equal to G3. Whatever B3, same as your G3. Now, what is G2? G2 is B3 XOR B2. So this is your G2. Okay, now what is your G1? B2 XOR B1. So this is your G1. Okay, now this is your B1 XOR B0. So this is your G0. So this is the logic circuit which converts actually a 4-bit binary to gray code. Any doubt, students? Any doubt? Please someone unmute and tell me. Any doubt on this? Do you all understand how you have constructed the design? Okay, so this is the way you can design any type of combination logic circuits. Okay, so we'll do another design. So let's say the question is so this is a little bit important question, students. So design a code converter which converts 4-bit gray to binary, just ulta of it. Whatever we have done, now we'll do just ulta of it. Okay, so here you can also understand that you would have to design a code converter. It takes a 4-bit gray code data. So this is your 4-bit gray code data as input. So these are my inputs. So gray codes will be like G3, G2, G1, G0. And this is actually your 4-bit gray to binary code converter. Okay, binary code converter. Okay, next it would produce a 4-bit output which is actually again binary code B3, B2, B1, B0. Okay, so this is your design. You need to design something inside. It will act like a 4-bit binary to gray code converter. Okay, so now what you need to do, you know this operation of it, how binary to gray code. I'll just tell you. I'll just revise the thing. Sorry, gray to binary. You already know that. How is it? Just I'll revise it. So let's say 1101 is a gray code. Let's say. Okay, how to find out binary code of it? It's very simple. This is my MSB and this is my LSB of the gray code. Just very simply, you just put MSB, kept MSB as it is. Now perform the XOR operation between these two. Okay, you perform the XOR operation between these two. Okay, then write the result here. So 1 XOR 1 is 0. Now perform the XOR operation between these two and write the result here. Okay, 0 XOR 0, 0. Next, perform the XOR operation between these two, then write the result here, 0 1 1. So 1001 is the binary code of this particular gray code. Okay, here what you are doing, whatever output is coming, this is making XOR with the next bit input of the gray code. Okay, so do you all understand? So this is the actually thing. If it is comes around two more question, what you need to do, you just need to construct this block diagram and make a logic like this. Gray code to binary is take an example. This is the way we can make it, and you can simply draw the logic diagram. How is it? Very simple, student. You can take G3 here as input. G3 is equal to your B3. Am I correct? Just I am copying the MSB. For your binary, MSB is also same as G3. Okay. Next, output of this is getting XOR with next bit input. Okay, so you can say that this is my XOR operation of the next bit. So this is my B2. Am I correct? Next output of this is going to be XOR with the G1 next bit input. So this is my B2. Next output of this will be making XOR operation with the next bit input G0. So this is my circuit which performs B3, B2, B1, B0. So this is actually the 4-bit gray code to binary code converter. So we can also prove this by making our truth table and K-map and all. Okay, but this will be the particular circuit at the end we can get. Okay, how we have got it? As we know this logic, by looking this logic only, I have designed this circuit, nothing else. Okay, just copying the MSB as it is. The output is performing XOR operation with the next bit input. Output, next bit input. Output, XOR operation with next bit input. Next output is coming. Okay. Any doubt on this, students? If it is 2 mark, you can write it up to this. You can get the mark. But if it is 5 marks, you need to perform the complete combination logic design. Okay, so for this you need to construct this truth table. This is your work, you have to do, students, truth table. And after that you need to find out the logic expressions for all these logic expressions from for B3. Okay, obviously you will get B3 as G3. Am I correct? Next B2 you will be get obviously B3 XOR with next bit input G2. Okay, are you understanding? Very simple. Next B1 you will get as a B2 XOR with G1. Okay, next B0 you will get as a, what you will get? B1 XOR with G0. So these are the expressions you will get. Okay, after that you can construct this logic. So how you will get? You have to perform the K-map. From this K-map you can you have to solve this 4 variable K-map. The inputs are your here G3, G2, G1, G0 are your inputs. Take those inputs and construct 4 variable K-map and finally find these logic expressions and finally draw this logic circuit. If it is 5 marks, you have to do all these things. Okay, if it is 2 marks, just you need to construct this block diagram. This is your block diagram, nothing else. Very simple. This is your block diagram, okay, of your combination logic design. Finally you write down one example to tell about what is the logic of the gray code to binary. Then from this you can directly construct a logic design. If it is a 2 marks, if it is 5 marks, you have to again construct the truth table. Take the 4 inputs are G3, G2, G1, G0, and outputs are B3, B2, B1, B0. Finally get the truth table, and from there logic expressions you can find out by just solving the K-maps. Okay. Any doubts, students? Any doubts? Please let me know. Please someone unmute and tell me any doubt. Srikar, do you have any doubt? Srikar,
No,
are you
sir.
there?
No, sir. Yes, sir.
Do you understand? Are you understanding
Yes,
everything?
sir. Yes,
Okay.
sir.
Then okay, do this. Okay, construct the K-map and find out all this logic expression and finally design it. Okay. If a 5-mark question, you have to do that procedure. Okay. So next part, we'll move to the next question of the code converter. Today we have to finish this code converter, and next 2 classes I'll finish it up this mocks, which will be cover up your complete mid exam portion. Okay. So it will be little bit more task we have today as well. So I may take some more 10 more minutes extra also. Please prepare for it. Okay. So next question will be your design a code converter. Design a code converter which converts 8421 code to its equivalent access 3 code. Okay, what you need to do? You need to design a code converter which converts 8421 codes to its equivalent access 3 code. Now the thing is, what is 8421 code? It's obviously a BCD code. Am I correct? So for BCD code, tell me what would be the maximum value you can get for this 8421 code. What is the valid BCD? Mainly 0 to 9 are my valid BCD. Okay. So you can understand here that my 8421 code is a 4-bit code. Am I correct? So this would be your design. You need to design a code converter which converts this 8421 code. Okay, 8421 code. 1 minute. Okay, you need to convert a 8421 code. Obviously 8421 code is a 4-bit. How is it? We have already seen actually. Let's say 9 is the highest BCD code. 8421 is what actually basically a BCD code. Okay, so 9, how we can write in 8421 code as a 9? So obviously you can see 9 means it is what actually, let's say 1, and this is 1, other 2 bits are 0. So this is actually 4-bit required to make a 9 in 8421 code. So that is the reason we would have 4 bits of 8421. Let's say those 8421 is a BCD code. These are 8421 is what? BCD code. BCD code means I can take it as a B3, one input, B2 another input, B1 another input, B0 another input. Okay, and what would be my XS3 code? So XS3 means what is the maximum BCD? 9 plus 3. So what is the XS3? 12 can be expressed in how? 1100. So we will require only 4-bit for XS3 as well. Understood? So we will be having E3, E2, E1, E0. So this is my XS3 output. This is my XS3 output. Okay, and this is my BCD, valid BCD input, or 8421 input. Anything your wish. So it actually converts. So this is actually the code converter which converts a 8421 code to XS3 code. So do you all understand why there is 4 inputs and 4 outputs? Because 0 to 9, 9 is the highest number for 8421. In order to represent 9, we require 4 valid binary bits, which is 1001. Similarly, the XS3 of 9 is the output, which is actually XS, the highest is 9, XS3 of 9 is 12. 12 can be expressed again in 4 bits. So that is the reason we have 4-bit XS3 code. Okay, so that is the reason I have 4-bit input and 4-bit output for designing this particular logic circuit. Okay, now what you have to do, you have to construct the truth table. So for the construction of the truth table, what you need to do, you need to know the behavior. What is behavior? Very simple. I have already told you 0. 0 is in one of the input, is a BCD code, 8421 code. If you want to access 3, it will be 0 plus 3. So what is 0? 0 0 0 0. What is 3? 0 0 1 1. So access 3 of 0 is 1. So this is the basic logic or behavior of the circuit we need to design. So what you need to do on this case, you need to perform the truth table. The truth table has the inputs B3, B2, B1, B0, and here the decimal numbers are what? The decimal numbers are, we can have from 0, 1, 2, 3. What are valid? 4, 5, 6, 7, 8, and finally 9. This much only. Okay, why? 0 to 9 are my valid BCD numbers. After this, these are not valid BCD numbers. Okay, so 0 to 9. So for 0, what are my B3? So this is my 8421 code. Okay, is my input. Okay, so 0 means 0 0 0 0, 1 means 0 0 0 1, 2 means 0 0 1 0, 3 means 0 0 1 1, 4 means 0 1 0 0. Next, 5 means 0 1 0 1, 6 means 0 1 1 0, 0 triple 1 7, 8 means 1 double triple 0 1 0 0 1. Okay, you just need to find out the XS3. XS3 means your E3, E2, E1, E0. Don't be get confused, students. Here, this is your MSB. Here, this is your MSB. So don't be get confused. Okay. So 0 excess 3 is 3. So 0, 0, 1, 1. Next, 1 excess 3 is 4. 0, 1, 0, 0. 2 excess 3 is 5. 0, 1, 0, 1. Very simple. 3 excess 3 is 6. 0, 1, 1, 0. 4 excess 3 is 7. 0, triple 1. 5 excess 3 is 8. 1, triple 0. 6 excess 3 is 9. 1, 0, 0, 1. So very simple. 7 excess 3 is 10. 1, 0, 1, 0. Okay. 8 excess 3 is 11. 1, 0, 1, 1. Next, 9 excess 3 is 12. So do you all understand? This is your truth table. Now you know the truth table. Finally, what you need to do? You need to find the logic expressions now. So in order to find the logic expressions, what you need to do? You have to perform either the K-map or you need to go for the Boolean algebra. Logic expressions. Okay. So what you need to do here? You need to find out logic expressions for your XS3 code E3. In order to do this, to find out E3, what you need to do? You have to perform a you need to perform what actually? You need to perform 4-bit variable kmap, 4 variable kmap. So obviously, why? Because in order to represent 9, we would require a 4 variable. Okay, because 3 variable can represent 0 to 7 minterms only. After 7, whatever may be, because here 8 and 9 also minterms are there. Obviously, we require a 4 variable kmap. Do you all understand? Because it's a 4 inputs, 4 variable kmap obviously required. Okay. So in order to construct this 4 variable kmap, it has 16 cells as like this, and the inputs are obviously here, obviously B3, B2, B1, B0. This is very important, student. This is very important question. B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Next, B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. Okay, now you know the place values over here. Now I just has to put those things over here. So you see here 0, 0, all 5 zeros. First, all 5 zeros, 0, 0, 0, 0, 0. Next, all 5 ones. All 5 ones means here 1, 2, 3, 4, 5. Now the question is here after 9 what is there? Okay, so you can see here up to 9 it is called valid BCD. Okay, after 9 what? It may be valid, it may not be valid. We don't require that actually, because we have a 8421 coding is my input. So obviously up to 9 only we would be requiring. After that, from 10 to 15, minterm 10 to minterm 15, it is actually don't care. Understand, students? So don't be get confused here. It is actually don't care. So you need to put don't cares for all these minterms. Okay, because we have valid BCD up to 9 only. After 9, M10 to M15 minterms are actually don't care. Please try to understand and please make it sure that you are understanding. Okay. Next thing, you need to group it up. For this grouping, what you need to do? This is one grouping, 8 minterms. You can take use of this don't cares. Then next step for this, you can have this grouping, and we can have another quads. Okay, so this is the way you can do. From this, what you got actually, this is your B3. From this you can get it as a B2 B1. From this we can get it as a B2 B0. Okay, then finally E3 is your B3 B2 B1 B2 B0. Okay, then finally we have got B3 plus B2 common B1 or B0. You can take it as like this. Okay, this is your final E3. Okay, any doubt on this? If there is no doubt, go for E2. Find again the same K-map, 4 variable K-map. Okay, so 4 variable K-map is like this. It has 4 variables B3, B2, B1, B0, and it requires 16 cells. For that reason, we have constructed 16 cells B3, B2, B1, B0. B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Next to B3 bar, B2 bar, B3, B2, B3 B2 B3 B2 bar. Okay. Now what you will need to do, just need to put those values. Very simple. How is it? 0 4 ones. You can take this 0 4 ones. Next 0 4 zeros 1. 4 zeros 1. So you can see 0 0 0 4 zeros 1. Again, other places don't guess. Okay. So now you can start grouping actually. So how you can group? You can group like this one quad, like this one quad, and also you can take this another quad like this. Okay. Next, only this much pair. Okay. So this is the way you can group it up. For this, what you have got actually from here. From here you have got this B2 bar B0. From this grouping, you have got it like B2 bar B1, and from this grouping, you have got it like B2 B1 bar B0 bar. Okay, then finally E2, we have got it like B2 B1 bar B0 bar B2 bar B0 and B2 bar B1. Okay, now you can take it B2 B1 bar B0 bar plus take B2 bar common here B0 or B1. You can take it like this, just minimizing the number of gates, nothing else. Okay, so this is your final E2. Next, similarly, you can construct for E1. Okay, and E1, I'll just write it down. You do it yourself. E1 would be coming like this. At the end, you will get it like this. E1 will be your B1 bar, B0 bar, B1 B0. You will come like this. So finally you can take it as B1 XNOR B0. Okay, if you can perform the K-map, you will get E1 like this. Similarly, E0, I'll just write it down. You have to do it at your home. These things I'm not doing because you have to complete lot of syllabus today. So this is your E1. Next, E0 will be very simple. You can see over here E0. E0 is look like a alternate zeros and ones, alternate zeros and ones. From this, you can come to know that very simple. E0 will be your B0 bar. You can take KMF, you can solve it up, you can get all these things. After this, you would have all these values E3, E2, E1, E0. Just you need to make the logic design. The last step is your logic design you need to do. So very simple. What you have to do? Very simple. I have already told you. You would be having your B3 here. Next, this is your B3 bar. Next, this is your B2, B2 bar. Next, this is your B1, B1 bar. Next is your B0, B0 bar. Like this way, you will take and design your logic design very well. Okay, just need to extend because we require four logic expressions. It's very simple. You can do it yourself also. I'll just design this E3 equal to B3 plus B2 B1 or B0. Okay, first I'll take B1 or B0. Sorry, B1 or B0. Next, it will be perform AND operation with B2. So this will be your B2 AND operation, and finally with B3 OR operation. So this is your B3 and the OR operation. So this is your E XS3 code. Okay, E3. Like this way, you can design the complete circuit. I'm not doing. You can perform. You can get E2, E1, and finally E0. Okay, you can get all these things. Any doubt on this, students? If there is no doubt, we'll move to the next part of our code converter. So, if you have any doubt, tell me. Any doubt? Students, any doubt? Bina, did you understand Bina? Bina, are you there? Any doubt? Bina, are you there? If not, I'm removing you from the class. Next, Naniti, are you there? Sriram Murthy, Sriram Murthy. Any doubt you have? Did you
Yes, sir.
understand? Hello,
No,
Sriram
sir.
Murthy, I am asking you. Did you understand the class? Okay, so we'll start the next part. Question. Next question will be the code converter design. This is again very important question. Design a code converter which converts. Design a code converter which converts access 3 code to BCD code. Access 3 code to BCD code. Okay, so this is my question. So what you need to do here, very simple. What is your BCD code? First of all, what is your output here? BCD code is output. BCD code means what? 8421. So which is have 0 to 9 are valid BCD. Am I correct? 0 to 9 is our valid BCD. Okay, so obviously how many bits required for BCD code? It has 4 bits, which is nothing else, B3, B2, B1, B2. So we can understand at the output side it has 4 bit, which is 4 inputs, each carries 1 bit. Okay, now access 3, tell me if it is BCD is a 4 bit, obviously access 3 is how much? BCD output minus 3. So obviously so what would be your access 3 coding? So maximum 9 means output will be 9 is highest BCD code is what you would be having. Highest BCD code is what? So this is access 3 means plus 3, and BCD code means it would be minus 3. Am I correct? So obviously for BCD code 0000, what would be the access 3 code? It would be plus 3. So 0011. So obviously we require 4 bits also for access 3, which is E3, E2, E1, E0. Do you all understand, students, why you require 4 bit input and 4 bit output? So this is your access 3 input and this is your BCD code output. So obviously we need to design a code converter which converts your access 3 code to BCD. So here access 3 code inputs are your E3, E2, E1, E0, and BCD codes are your B3, B2, B1, B0. So this is the logic circuit you need to design which converts the XS3 code to BCD code converter. Okay, so now truth table is very important, students. So do you all understand the thing what you need to do? So here truth table, you can just see here how I am going to construct a truth table. Tell me XS3 is 0000. What would be the BCD? So what would be the BCD, students? So this is your XS3, E3, E2, E1, E0. Obviously, we here how many inputs possible? It's a 4 variable, so 16 possible combinations possible. I'll just write it down here: 0000. Then this is BCD, B3, B2, B1, and B0. Here this is BCD code and this is your XS3 code as your input. Now tell me what is XS3 code? XS3 code is plus 3 of this BCD, and what is BCD code? It is 8421 coding, which is minus 3 of this XS3 code. Am I correct? Do you all understanding or not? So 0000, what would be the XS3 code of it? It is already XS3. 0 is XS3, XS3. So obviously what would be the BCD? It's don't care, students. Why? Because 0 if I do minus 3, it's not possible. It's very difficult to express minus 3 in this. So obviously we got don't cares. Okay. Now tell me if it is 0001, then what would be my XS3? It is again all don't cares. Okay. Next 0, 0, 1, 0, 2. Okay. What would be the BCD? Obviously, again, this is all don't guess. Now, 0, 0, 1, 1. It's excess 3. Means it's already 3. You can do minus 3 to get it. So, what would be BCD? 0, 0, 0, 0. Just you need to perform minus 3. So, we got, this is actually what? 3 decimal 3. If you perform minus 3, 3 minus 3, you got 0. Do you all understand now? Or any doubt, please let me know. This is very important, students. I will surely ask this type of questions in main exams. Okay, mid exams. Okay. So 0, 0, 0, 1. Next to go for 0, 0. So 0, 1, 0, 0. So what is the BCD code of it? 0, 1, 0, 0. So this is 4. 4 means 4 minus 3, 1. So this will be 0, 0, 0, 1. Understand? This is the way you need to just construct 0, 1, 0, 1. So this is 5. 5 minus 3, 2, 0, 0, 1, 0. Next is 6, 0, 1, 1, 0. 6 means 6 minus 3, 3, 0, 0, 1, 1. 7 means 0, 1, 1, 1. So in order to 7 minus 3, 4, 0, 1, 0, 0. Do you all understand how I am constructing the truth table? Once you construct the truth table, it's very easy to design the circuit, students. Please try to understand. If you understand the truth table, it's more than enough for you. Okay? 1 triple 0. 1 triple 0 is 8. 8 minus 3 is 5. 0, 1, 0, 1. Next to 1, 0, 0, 1. This is 9. 9 minus 3 is 6. 0, 1, 1, 0. Okay, 1, 0, 1, 0, 10. 10 minus 3 is 7, 0, triple 1. Okay, next 1, 0, 1, 1, 11. 11 minus 3 is what? 8, 0, 8 means 1 triple 0. Okay, 1 triple 0. Next 12. 12 means 1, 1, 0, 0. 12 minus 3 is what? 9. 9 means 1, 0, 0, 1. Okay. Now, very important, 1, 1, 0, 1. 13. 13 means 13 minus 3 what? 10. Is 10 is present in my BCD? No. Okay, 10 is not possible because valid BCD is 0 to 9 only. So 10 is what? All don't cares. Do you all understand? So it's very important. Valid BCD is always 0 to 9. This is your valid BCD. So after 9, we have already reached for 12, it's 9. So after 9, all will be your don't cares. Okay. So similarly for 13, next to 14, 1, 1, 1, 0, which is actually 14. All these are don't cares. Okay. Next to 15, 1, 1, 1, 1. All these are again don't cares. Do you all understand? So very important. Truth table is very important. If you understand the truth table, then it's very easy for you to design the circuit. Okay. Anytime if you construct this truth table, this is very easy. So what do you understand from here? For the min terms M0, M1, M2, it has don't cares. For B3, B2, B1, B0. Similarly, for minterms M13, M14, and M15, all these BCD codes are don't cares. Okay. Now, what you need to do? You need to find the logic expression to design the particular logic circuit. So, this is my logic expressions. What I need to do? Just very simple. I just need to find out for B3. So, it's again a 4 variable KMF. So I'll just construct a 4 variable KMF. Here inputs are what actually? Inputs are your XS3 inputs E3, E2, E1, E0. So this is my E3, E2, E1, E0. Next is my E1 bar, E0 bar, E1 bar, E0, E1, E0, E1, E0 bar. Okay. This is my E3 bar, E2 bar, E3 bar, E2, E3, E2, E3, E2 bar. Okay. Now I can just has to put those values. Okay. So for this case, what we would have, first three are don't cares. 0, 1, and 2 are don't cares. And other places, what is the, you can see this actually M M3 to M8, all are zeros. M3 to M8. Okay. Next M9. M9 is what? M9 is also 0. Yeah. M9 is also 0. Next it is 1. Okay, next it is 1. M10 is M11. Next is 1 1. Okay, so this is your also 1, and this 0, and other three places are don't care. Okay, 14 15 16 13 14 15 also don't care. Okay, so this is the way we have got finally. And finally what you have to do, you start grouping it. For grouping, this is one grouping I can take as a quad, and any quad is possible. No, this is another grouping. So we have got it here like E3, E1, E0. Okay, and we have got it here E3, E2. So finally we have got B3, which is nothing else, E3, E2, or E3, E1, E0. So we can take it as E3 common here, take it as E2, E1, E0. You can do it like this. Okay, this is your finally B3. Like this way, we can construct this KMF and find out all these values. For B2 also, you can do yourself, very simple. Take this for B2. Again, you can construct this KMF. B2 will come up like this, like expression. I'll just make it up here. E2, E1 bar, E2, E1, E0. Next, E2 bar, E0 bar. Okay, this is your B2 expression. If you solve this KMF, you will get like this. Very simple. You know this how to solve KMF. We have done multiple enormous number of KMF, so you can do it up yourself. Okay, so again, B1 will be your E1 bar, E0, E1, E0 bar, and you have got it from this E1 XOR E0. Okay, this is your B1. So you have XOR E0. Next, B0. At the end, B0, we can find out B0, which is actually E0 bar. Okay. Okay, do you all understand? So from this, you can have all this B3, B2, B1, B0. So B3 is with you, B2 is with you, B1 is with you, and B0 is also with you. Now we can easily construct the logic design. Any doubt on this? If there is no doubt, we can go for the next last part of this code converter, which is very important. And this question I'll ask you in the mid exam. Okay, so please try to understand. The question is, design a BCD to 7 segment decoder which displays BCD numbers. What are the valid BCD numbers? 0 to 9. So this is the question. The question can be modified also, like design a BCD to 7 segment decoder which displays your department. Okay, department is what? Electronics and communication engineering. Okay, like this it will display. So these are valid application, basic applications of it. So before that, before starting the thing, what you have to do, you have to design a BCD to 7 segment decoder. I'll tell you all these 7 segment is what. BCD, you know that what is valid BCD? 0 to 9. So obviously, in order to express the BCD, we would have 4 bits. What are those 4 bits? B3, B2, B1, B0. Okay, so this is my BCD input. Do you all understand? My output is what? 7 segment. So 7 segment means how many output we are going to see now. Don't worry, students, just please concentrate, very important. 7 segment decoder, this I have to design here. Okay, so please see here, what is my 7 segment? What he is telling here, mainly you need to construct a 7 segment to display the BCD numbers 0 to 9. Okay, so tell me how these 7 segments, it has actually 7 segments at the, which are actually LEDs. So 0 can be expressed as what? This way. Please see here, students, very important, I am telling. Okay, 0 can be expressed in this way. Okay, 1 can be expressed in this way. 2 can be expressed. Okay, 3 can be expressed. 4 can be expressed. Are you understanding, students? Very important question this is. 5 can be expressed. 6 can be expressed. 7 can be expressed. 8 can be expressed. you can see in 8 all these 7 segments are using. Okay, 4 plus 3 7. Okay, and 9 can be expressed. Okay, do you all understand? So these are my valid BCD numbers, which is actually, this is your 0 1 2 3 4 5 6 7 8 9. Do you all understand? Now you can see that what is the maximum input outputs here you require. So mainly 8 is 8 requiring all 7 segments. So you can give the name as a like this. So you can give it name like this, students. Start from clockwise: A, B, C, D, E, F, at the end G. Okay, all of you understand? Like this way you can give the names. So here also for 0, A, B, C, D, E, F. For 1, B and C present, students. Okay. Next, A, B, C is absent, D, E, F is absent, G. Okay. For 3, A, B, C, D, and G. Okay. For 4, B, C. Next, this is F, G. Okay. For 5, A, B is absent, C, D, E is absent, F, G. For 6, A, B is absent, C, D, E, F, G. Okay. For 7, A, B, C. For 8, we have already done A, B, C, D, E is absent, F, G. Do you all understand? So how many outputs here? You can understand here 7 outputs. What are those outputs? 1, 2, 3, 4, 5, 6, and 7. So outputs are A, B, C, D, E, F, G. So these are my 7 segment display outputs, 7 segment decoder output. Okay, do you all understand what is your input? BCD input and 7 segment decoder output. So obviously you have to design such a way that once you put input 0 1 2 3 or any of these inputs 0 1 2 3, any valid inputs of BCD, it will glow the LEDs in this fashion. Okay, so do you all understand what to do? So here your truth table would be like this. The truth table will be very simple. So truth table, it has BCD input, which is B3, B2, B1, B0, and it has 7 segment decoder output as A, B, C, D, E, F, G. Okay, this is your 7 segment decoder output, and this is your BCD input. Okay, so your valid BCD is 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so for this, what is A? In 0, this is my 0. In 0, A is present? Yes, A is present. Okay, so you can write down 1 over here. In 0, B is present? Yes, C is present. Everything is present except G. G is only not present. Put 0, and other places all are 1. Understand how I have constructed truth table? Very simple. Now 1. In 1, what are present? Only B and C are present. Only B and C are present. B and C. Other places just simply 0. Okay. And in 2, what are present? C is absent and F is absent. C and F are 0. C and F are 0. Other places 1. Okay. Next to 4, what are present in 4? So sorry, D. This is 2, na? In 2, what is absent? Only, yeah, C and F. That correct. C and F. Next, now 3. In 3, what is absent? Your E and F are absent. In 3, E and F are absent. Okay. Just you need to put absent for E and F. E. So where is E? So your E and F for absent, other places 1. Okay. Now 4. In 4, what is absent? A is absent. A, D, E. A, D, E absent. A, D, E. Other places 1. Okay. For 5, 5 only B and E. B and E absent. B. B and B and E. B and E absent. Other places 1. Just you need to find out those things, nothing else. In 7, in 6, only B is absent. In 6, only B is absent. Other places 1. Okay. And in 7, ABC only present. ABC is present. So I can put ABC. Other places 0. In 8, all the things are present. So you need to put all ones over here. Okay, do you all understand? Now for 9, what is absent? Only E absent. Only E absent, everything else is 1. So do you all understand how I have constructed the truth table? Very important, students. So after this, what you need to do? You need to find out the logic expressions for all these A, B, C, D, E to F. Okay, to get the final logic circuit. So this is what you have to do for A. For A1, I will do, others you have to do, students. So for A, what are the things you require over here? So you can see your valid BCD is what? 0 to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. After 9, all these were what? From 10 to 15, because from min term 10 to min term 15, what is that? All will be don't guess. Okay, this you please remember, because your valid BCD is always from 0 to 9. In order to find out the expressions for A, you require how many variable KMF? A 4 variable KMF. Why? Because your 4 inputs are B3, B2, B1, B0. So you will have actually your 4 variable KMF here: B3, B2, B1, B0 are inputs, and it requires 16 cells for M0 to M15 minterm. So this is your B3, B2, B1, B0. This is your B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Okay, this is your B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. Okay, so you know the minterm positions, and you can just has to put this. This is 1011. So you can just put those values 1 0 1 1. Next 0 triple 1 0 triple 1. Okay, next 1 1 1 1, and other places from 10 to 15 all are don't guess. Okay, just need to put like this. I'll do only one, you do yourself all these things, students. Practice it at home, it's very important. So for the grouping, you require this one grouping, and you can take all these 4 corners, another grouping. Okay, next you can have these 8 minterms also, another grouping. Only one this is left out, take this quad. So how many groupings are there? 1 2 3 4, total 4 groupings. So finally from this, what you got here? B3 and only B3, am I correct? From this B3. Okay, from this 8 minterms combinations you got B3, and from these 8 combinations you got B1, and from these corners you got actually what? Actually B2 bar, B1 bar. Okay, B2 bar, B1 bar, uh, B2 bar, B1 bar, or B0 bar? B2 bar, B1. Huh. Correct. Next, from this you have got it as a B2 B0. Okay, B2 B0. Okay, so finally what you have got? A, you have got it like B3 B1 B2 B0 B2 bar B1. Okay, so this is the expression. Similarly, you can find out for all these B, C, D, E, F. So I'll just write down for B, you'll get like this: B2 bar XOR B1 XOR B0. Okay, next for C, if you solve for KMF for C, you would get like this. C would be your B1 bar or B0 or B2. Okay, next D you will get like this: B3 B1 B0 bar B2 bar, B0 bar, B2 bar, B1, B2, B1 bar, B0. Okay. Next, E you will get like this. E will be your B1, B0 bar, B2 bar, B0 bar. Okay. For F, you will get like this: B2, B1 bar plus B3, B1, B0 bar. Next, B2 bar, B1. Okay. Next, finally, G you will get like this: B1 bar, B0 bar, B2, B1 bar, B2, B0 bar, next B3. Okay, all these expressions you will get from, if you solve this KMF for A, B, C, D, you would have already all these things informations with you. Just you need to solve the way I have done for A. You can get all these expressions. Then finally you start designing the thing. Very simple. You just take B3, take this as a NOT gate. This is your B3. B2, take it as another NOT gate, which gives you B2 bar. B1, take it as a NOT gate, which gives you B1 bar. B0, take it as a NOT gate, you will get B0 bar. Okay, all these things. Then you just design it, and you can get a BCD to 7 segment decoder. Any doubt, students? If there is no doubt, I'll just give you another homework to you. Please try to do this. So the homework is design a hexadecimal to 7 segment decoder. 7 segment decoder which displays a hexadecimal number. Now tell me, what is hexadecimal number? Do you all understand the question? Just I'll give you hint before leaving the class. Hint is, what you need to do, you have to design a hexadecimal number. So hexadecimal number is what? 0, 1, 2, next 9, A, B, C, D, E, F, 10, 11, 12, 13, 14, 15. So this is your hexadecimal numbers. We know how to do with 0 to 9. Just now we have discussed. For 0 to 9, this is the way. Now only you need to know A, B, C, D, E, F. Okay, am I correct? So what you need to do, A can be written as what? A can be written in this way. So can I write down A like this? Yes. Okay. So for this, you would have A, B, C, D is absent, E, F, G. Okay. Next, B. B can be written like this. I can make small b, or you can make big B also, your wish. But if you make a big B, it will be merged with 8. You cannot understand the difference between 8 and capital B. That is the reason you need to do a small b. Okay, small letter B. For that reason, what you have to do? C, D, E, F, G. Understand why I have done a small b? Because there will be a confusion between 8 and capital B. That is the reason I have used the small b. I have just written the hint also here. Okay. Next, C. C can be drawn. How? C, you can do a capital C, not an issue. Okay. So for that case, what you need to do? This is A, B and C absent, D, E, F. Okay. Now D. D again, if you do, it will merge with 0. So that you can do with a small d. Okay. So this is your D, which is B, C, D, E, G. Okay. So why I have done small d? Small d, because 0 and capital D will merge. Okay, you cannot identify what is 0 and what is capital D. So that is the reason I have done small d. Next, E. E can be drawn a capital E, not an issue. Okay, so here A, B, C absent, D, E, F and G. Okay, now F. F can be a capital F, not an issue. Okay, A, B, C absent, D, D, E, no. Okay, A, B, C, D is absent, E, F and G. Understand? This is the way you need to design all these hexadecimal numbers. 0 to 9 we have already done here, and from this you can find out all these A, B, C, D, E, F and construct the truth table. Okay, after that find out the logic expression, then find out the logic design. This you have to do, students. Very important. One of these, out of these two, one question will come in the exam. Any doubt? If there is no doubt, we'll just stop over here. If there is doubt, please let me know. If there is no doubt, I'll just stop over here. Any doubt? Please someone unmute and tell me.